Hey everyone, so we're going to continue with our discussion about momentum and in particular focus on probably the most important aspect that you're going to be dealing with, which is conservation momentum. Really quickly, I'm going to split this video into two parts. The first part, I'm going to talk about the concept of conservation momentum as well as do a few practice questions. And then the next video, I'm going to continue doing more practice questions. Because of that, both these videos should be a little bit on the shorter end. Now, as the name implies, conservation momentum basically is referring to the fact that momentum is conserved, or in the sense that if we look at the total momentum before objects interact and after they interact, they should end up being the same. So this is one of a few of the main conservation laws in physics. You should have learned about a lot of these from chemistry and other science classes. Like, for example, there's conservation of energy, the fact that energy can't be created or destroyed, it always has to come from something. So if you start with a certain number of joules of energy, like 5 joules of energy, when you do some sort of chemical reaction, you should end up with 5 joules of energy again. It might be in a different form, but it's the same amount altogether. Same thing, the other type of conservation law that we have is conservation of mass, that mass cannot be created or destroyed. That if we have a certain amount of mass before a interaction, before some sort of reaction, like a chemical reaction, we should have the same amount of mass afterwards. There's also another one, which, if you recall back in chemistry, when you were balancing equations, you had to recall conservation of charge as well. That if you counted all the charges on one molecule on one side of the equation, the number of charges should be equal on the other. So this is along that same idea that we're going to set up an equation, just like with the balancing equations in chemistry, where we're going to be looking at the momentum that happens before an interaction and what happens to the momentum after. And they should end up being the same, and this is how we're going to solve our problems. Now, as you can see from the images, this is usually going to be used in the concept of collisions, like car crash collisions, people colliding, billiard balls, or basically any type of objects colliding together. We're going to look at the momentum before the collision, the momentum after the collision, and see what's going on. All right. So yeah, like I said, momentum is one of the four main conservations that are always occurring in physics. You do want to make sure that you remember these four conservations because it comes up a lot on the Regents where they'll just ask that blanket question of, hey, what's something that's conserved here? And basically saying one of those four things will always get you the answer, regardless of the context. Typically, something like mass, energy, momentum will pretty much always get you the correct answer. And like I said, charge is another one that's also always conserved. So the equation that's on the reference table is this: P before equals P after. That the momentum before collision is equal to the momentum after the collision. If you're doing a problem and you find that the collisions aren't equal, that means that you're making a mistake either with your calculations or you're not including all the objects that are involved. Now, this equation, as I said, it is on the reference table, but by itself it's not useful. Its only purpose, for the most part, is it's going to count as the equation that you show when you're doing your free response questions. So what you're going to do is you're going to write this and then you're going to do some other stuff, which I'll explain in a second. Now, in our collisions in this class, we're mainly going to focus on the collisions between two objects, which means that if you recall, the equation for momentum is mass times velocity. So we have two objects before a collision and we have two objects after a collision. So that means we have an m times v for the momentum of one object, an m times v for the second object before the collision. We have an m times v for the first object afterwards, and an m times v for the second object after. So it's going to look something like this. So again, we have two objects, their momentums before the collision, the momentums after. And if we plug in m times v, we end up getting something like this. So the equation would be said as m1v1i plus m2v2i, m1v1f, m2v2f. This is not in the reference table, and honestly, it's kind of a handful. A lot of people have trouble with using this, so I've come up with a slightly better way of dealing with this. Basically, what I want you to do instead is draw out the collision. So let's say you had an example like this. A car traveling to the right collides with a truck that's at rest. Afterwards, the truck begins to move and the car comes to rest. Well, what you would do is you would draw what happens before the collision. We have a car traveling to the right and a truck that's at rest. All right, so that's what that image is showing. It's showing what they tell us. We find out that they collide, and then afterwards, we know that the truck moves to the right and the car comes to rest. So we draw the car by itself and the truck with an arrow to the right. It's definitely important that you make sure that you're drawing the arrows in the right directions, as you'll see later on. And then from here, what you're going to do is record the mass and velocities for all three of these. So you'd record the mass of the car, the velocity of the car, mass of the truck, velocity of the car, underneath each of these diagrams. Then you would use those to find the momentum, and you would say that the momentum of this plus the momentum of this equals momentum of this plus momentum of that. I'm going to show the first one, so we'll see how it works in a second. Now there's a few different types of collisions that you kind of want to keep an eye out for. The first one is the bouncing collision. This is basically where we have two objects that hit into each other before, and then when after they hit, they still kind of have their own momentum. So this is a perfect example. These are very common. A lot of times what they're going to do is set one of these either starting at 0 or the other one ending at 0. So they do try to minimize how many terms you have. There's sticking collisions. So this is another very common one where you have objects colliding together, but instead of kind of bouncing off each other and remaining as two separate objects, here they're going to stick together and then move as one object. And the main idea here is that their final velocity is going to be the same because they're now one object. We'll see how we kind of end up dealing with that later on. And then there's the reverse of the sticking equation, which sticking scenario, which is the explosions, where they start as one object and then they split off into two different objects afterwards. And here, the idea is that they start with the same initial velocity and then they end as two separate objects. A lot of times you're going to see this with cannons, bullets, recoil speeds, anything like that is referring to an object that's exploding out. And then, like I said, I know I say here that you're going to start with this equation, but you actually really want to start with the P before equals P after equation. Regardless of what you do, that's what you start with. All right. So, I'm going to pause video right now, work on this for a second, try to answer it, and then we'll go over and I'll show you how you would use the whole process. All right. So as I said, the main step is to draw out what's going on. In the first step, we're told that the 0.2 kilogram cart is moving to the right and that cart A, which is 1 kilogram, is at rest. They end up colliding. We're told that cart B, which is the 0.2 kilogram, comes to rest and the 1 kilogram moves to the right. So this is a very basic description of what's going on. Underneath each of the objects, I'm going to record their mass and velocity. So the mass of the first object is 0.2 and its velocity is 10. The mass of the second object is 1 kilogram and its velocity is 0 because it's at rest. After they collide, we know that the 0.2 comes to rest, so its velocity ends up being 0. And the velocity is unknown for cart B. Now what I'm going to do is I would write this. So this is pretty much what you want to show as far as the show all work aspect of the free response. So you would write P before equals P after. Then what you're going to do is just multiply these numbers. So I do 0.2 times 10, making sure I include my units, plus 1 times 0. The boom tells me it's an equal sign. And then it's 0.2 times 0 plus 1 times x. So this is my whole momentum equation. And again, in order to get the full credit, you have to show this equation and this setup with the units. From here, you can kind of clean it up, get rid of you can ignore the units after your initial substitution. So this just becomes 2 equals 1x, which tells me that the final velocity is 0.5 meters per second. Now, this diagram is good for you. I don't need to see the diagram, but as far as what I would need to see as a free response, it's everything from p before equals p after all the way down. If you show me anything less than what I have here, you are not going to get full credit. So I just want you to keep that in mind whenever you're doing problems, whether it's in labs or on tests or whatever. If you are getting points off, chances are it's because you're not showing me this full amount of work. All right, here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so we're going to do the same thing. We're told that cart B is moving to the right, collides with cart A, which is at rest. They collide and go boom. And this time they tell us that cart B actually does end up moving after the collision. Now, they don't explain what direction it goes, but that doesn't matter. We're just going to say it goes to the right, have all the arrows to the right, just to make our lives easier. Once again, I'm going to record their mass and velocities, still 0.2 and 10, 1 and 0, 0.2 and x, and then 1 and 3. So these are their masses and velocities. Once again, I start with my p before equals p after. I multiply the mass and velocity, so 0.2 times 10, 1 times 0, 0.2 times x, and 1 times 3. Make sure to put your units there. Just going to clean it up a bit. So this is 2 plus 0, 0.2x plus 3. Move things around, do some basic algebra, and you end up getting that x equals negative 5. So this means that the final velocity for cart B is going to be 5 meters per second to the left. So my arrow, which was drawn to the right, should have actually been drawn to the left. But remember, the diagram doesn't matter. It's only meant for you to record stuff. So you would say that the velocity is 5 meters per second to the left. Okay, here's the next question. Pause the video, work itself, and we'll go in a second. All right, so here it changes up a little bit. We still started with the same scenario. We have one object moving to the right, hits into an object that's at rest. They collide and boom. But now they tell us that they get stuck together and they're moving as one. So what I'm going to do is I'm going to draw it as one big single object. I do the same thing. This time they change the velocity to 5 meters per second, and the mass is also now 2. The cart A is going to be 1 and 0. And then for this one, we're going to do 3 kilograms and x for the velocity. So do the same thing, p before equals p after. 2 times 5 plus 1 times 0 equals 3 times x. Make sure to include your units. Clean it up. We get 10 equals 3x. Divide the 3 over, and we get that the final velocity is going to be 3.33 meters per second. So after they collide, that's a speed it's going to move with. And then this will be the last question, so pause the video, work itself. We'll go over in a second. All right. So here they give us a diagram, and a lot of times with multiple choice questions, they usually will give you an initial diagram. We have the 8 kilogram object and the 4 meters per second to the right. We have the 4 kilogram moving 6 meters per second to the left. I don't need to redraw that. You could if you want, but we're going to take that. It goes boom. And then we don't know their final directions, or at least for the 8 kilogram cart. So we'll just say that everything goes to the right afterwards. Again, we don't know. We'll figure out that later. I record their mass and velocities. So cart A is going to be 8 and 4. Now here's where I have to be very careful. And like I said, we're drawing the arrows in their directions for a very specific reason, because direction matters. 4 to the right and 6 to the left needs to be shown in their values. So when I write the velocity, this should be negative 6 meters per second. Then we have 8 and x over here and 4 and 3 over there. So again, that's also why you just kind of guess that everything moves to the right afterwards if you don't know their directions, mainly just so that you don't have to worry about the sign. But if you know that something goes in a different direction, you have to make sure that you put a negative. If you didn't put a negative, you'll get the question wrong. You do p before equals p after. You multiply everything. 8 times 4 plus 4 times negative 6 equals 8 times x plus 4 times 3. Make sure to include your units. Clean it up a bit, so we end up getting 32 minus 24 equals 8x plus 12. Do some basic algebra again, and you end up getting negative 0.5 meters per second, which again, the negative tells me it's in the opposite direction of everything else, so it should be 0.5 meters per second to the left. And that's pretty much it. We'll do a few more practice questions, see kind of how much trickier they can get. But this is going to be the crux of the main concept of momentum, this conservation momentum aspect. Everything else dealing with just the momentum equation itself or the impulse equation are typically going to be left off as plug and chugs. This is the main one that you are more likely to see as free response questions and possibly even multiple choice questions. All right. If you have any questions, feel free to let me know. Otherwise, I'll see you later. Good luck and have a great day.